Hello, physical science. It's Miss Stone Day. Today we're going to be talking about the periodic table, one of my favorite units to be talking about in this class. The essential question is, how do chemists or any scientists use a periodic table as a scientific tool? In this lesson, we're going to be learning about the introduction of the periodic table, organization, where are the metals, nonmetals, metalloids, and we're going to learn about some of the chemical families on the periodic table. Let's get into it. All right, so the periodic table is a chart that organizes the elements. These elements, I believe there's 118 of them, are what make up every single thing that we know about, everything in the entire universe. Your body, the chair you're sitting on, the computer in front of you, the air that we're breathing, everything, okay? It's just like when you have 26 letters of the alphabet make up libraries of books, okay? With just 26 letters, we can make up any book. We can write anything we want. And so we see the same thing with these 118 elements make up everything that we know. So the elements are organized according to their increasing atomic number. You may say, what's an atomic number? When you look at the periodic table, it's that whole number, usually at the top, sometimes at the bottom of the box. And these are the number of protons. We have not gotten down into the anatomy of an atom, but we will. But know that this whole number is called an atomic number, okay? Also, they're arranged according to their chemical and physical properties. So when was the periodic table created? It was created by Dmitry Mendeleev in 1869. He was a Russian chemist, and in his time, not all the elements were known. We did not know what an atomic number was then either. He didn't know about the protons or the electrons. So, you say, okay, well, let's just put them in order from low number to high number. At the time, that it wasn't that obvious because we didn't have all the information that we have right now. So, in his time, there were only 60 elements discovered. And he thought, maybe there's more. He was very obsessive. He had all the elements written out on cards, and he would move the cards around, and he was like, I'm going to find a way to organize this list of elements. And luckily, he did do that. So when you look here, you'll see that, the periodic table predicted. So what his genius is, he said, wait a minute, maybe we don't know all the elements right now. And there were only 60 now then. Right now there's 118. So what he did was he left room for elements that he predicted would be discovered in the future. So if you look at this table, the blue elements are the ones that he did not know about, okay? And he said, for example, GE under TI, under titanium, he said, I don't know what this element's going to be called, but I can tell you the properties of this element. It'll have this mass. It'll have he could predict the density. He could say it was a solid. He knew all kinds of things about it. And when someone actually did discover this element, he said, wait a minute, no, some of your numbers are wrong. It should be, your mass should be this. Your boiling point should be this. And he was right. He predicted the characteristics of the elements unknown. It's just like when you were working on a jigsaw puzzle and there's a piece missing and you have all the pieces around it, but you don't have that piece. Well, I can tell you its kind of shape, what the shape of it is. I can tell you what color should be on that piece because it's missing, but it creates the rest of the puzzle. So that's the same thing what he did with these elements, was he predicted very accurately the properties of these unknown, yet to be discovered elements. So each element in the periodic table is represented within a box. Oops, sorry. An element box which contains the following basic information. You'll see that whole number, which is the number, the atomic number. It's always a whole number. You'll see an element symbol, always, 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 capital first letter, second letters, always lowercase. If you were to hand in a paper that said big B, big E, and your answer was beryllium, that would be wrong. It needs to be a lowercase. Here we have the element name. And the element names are kind of funky. They're kind of like, it's almost like a new language. And the atomic mass is always larger than the atomic number, and it always has decimals, okay? atomic mass, atomic number. Don't get those two mixed up. And last of all, not every time, but some of the periodic tables will have an oxidation number on it. All that means is beryllium usually forms something with a +2 charge. And we're going to go into that, touch on that today, but go into that a little bit more later. Okay, so it's always a positive or negative sign. Things gain the electrons, then it would be negative. So if you were in my class, you'd have a periodic table in front of you, and I would say, draw the element box for the element that has the atomic number of 107.87. You would go to your periodic table, you would find the one with the atomic mass of 107.87, and you would fill in the information. And the next one says, draw the element box for the element that has a symbol PT. You would go to the periodic table and you would find out what PT is, and you'd fill it in. So the element with 107.87 is silver. The symbol for silver is not Si like you would think it is. Si is actually silicon. Silver is Ag, it stands for argentum, I believe. And that, I want to say it's Spanish, but I could be wrong. A lot of the element names and the element symbols, they don't match like you think they would. That's okay, you'll get to know them. The next one, PT, is platinum. And you can see the funny thing about platinum, it says +4, +2. Sometimes it loses 2 electrons, sometimes it loses 4. We're going to talk about that in another unit. So, organization of the periodic table. The periodic table is arranged in columns and rows. So each column on the periodic table, when I talk about column, I'm talking about vertical. These are called groups. I will also call them families. I will interchange those two words, groups or families. So how many groups are on the periodic table? If we look at the numbers on the top, there are 18 groups on the periodic table. Each row in the periodic table, horizontal row now, is called a period. How many periods are there on the periodic table? You look at this on the side, they're numbered 1 through 7. There are 7 periods on the periodic table. What I want you to note is down at the bottom, I know somebody's raising their hand virtually and saying, wait a minute, wait. There's 2 rows down at the bottom that are not counted in here. So the actual periodic table, those 2 rows at the bottom would be inserted. It says number 57, and then it goes, I'm looking at period number 6. It says 57, and then it jumps to 72. That's where that top row on the very bottom would be inserted. And the same thing with the next one that says AC number 89, and then it goes to 104. That bottom row would be inserted in there, which would make the periodic table go from here to here, and it wouldn't fit on my wall. So what we see in the periodic table is to make it more convenient to fit on posters, is they pulled out those 2 rows at the bottom, okay? No worries. They go into period 6 and period 7. All right, so there is a zigzag that separates the periodic table into 2, it breaks it into 2. So I'm hoping that you have your blank periodic table, or this is what you'll be taking notes on, and I want you to fill in, darken that zigzag line, please. The zigzag line is also called the staircase. And it's basically, I asked you to darken that in, it's basically to separate the periodic table. To the left of the staircase, you will find the metals. Even those 2 rows at the very bottom that are not inserted into the periodic table are metals. What I want you to note here is that most of the periodic table, most of everything that makes up anything and everything in this universe is made up of metals, okay? And actually, I do want to add number 1, hydrogen is not a metal. We'll talk about that in notes later, but it is a non-metal, but it's put on that side, it's the one exception. To the right of the staircase, you will find the nonmetals. There are not very many nonmetals, okay? Kind of interesting, I don't know, mostly metals, or mostly made out of metals, and there's a few nonmetals. So if you can label these sections on your periodic table, that would be awesome. So it says to the right of the staircase, you'll find all the nonmetals except for the element, and I just spoiled it, hydrogen. Hydrogen's on that side of the periodic table. We have reasons for it. It's put on the top of family number 1 or group number 1. It's really not a part, but it needs to go somewhere. It's kind of unique, so they put it there. So, except for hydrogen, which is a non-metal found on the left side of the periodic table. This is the one exception for metal and non-metal. Please make sure you note that for sure. So you're going to shade in hydrogen on your periodic table, and you're going to label it as a non-metal. So here we have the zigzag, and it says elements to either side of the staircase are called, notice it's all been highlighted except for aluminum. These are called the metalloids. The metalloids? Yeah, so we have characteristics of nonmetals. They act a certain way. Metals act a certain way. The metalloids kind of act in between, okay? Kind of half metal, half non-metal. And there are 8 of these elements. Again, if you're touching the stairs, you're a metalloid unless you're aluminum. Aluminum is a definite metal. It has no properties of a nonmetal. So shade in your metalloids on your periodic table, and you are going to label them. Boron, silicon. All you need to do is put in the element symbols. You don't need to write the words. AS, SB, TE, POAT. All right, metals, nonmetals, metalloids. And I keep saying acts like a metal, acts like a nonmetal, behaves like. What does that mean? What are the properties of metals? All metals are solid at room temperature, except for mercury, which is a liquid. Mercury is the only liquid metal, and on the whole periodic table, there are only 2 elements that are liquid, and mercury is one of them at room temperature. All right, many metals are, what's that word mean? Lustrous? That means they're shiny. You had that in the last unit. They're silvery mostly. Some of them are kind of yellow. Some are kind of an orangey. Silvery in color. What is that called when you can turn it into a wire? They're ductile. And you can hammer it into sheets. What's that? Malleable. And let's see, they're inside wires. They conduct electricity. They are conductive, electricity and heat. And some are even magnetic. Okay, so these are characteristics of metals. This is how metals behave. So when I say behave, this is what I'm talking about for metals. Nonmetals, most nonmetals are actually gases. Except for, there is one nonmetal that is a liquid, and that is bromine, which is a liquid. And I want you to look at this picture that looks like a bunch of neon lights. Notice that those are all from family number 18, okay? If you look at family number 18 on a periodic table, you'd see it goes from helium down to xenon. Okay, and 5 nonmetals, which are all solids. So we have solid, liquid, and gases for the nonmetals. The solids are carbon, phosphorus, sulfur, selenium, and iodine. Okay, very small list. That's a very small list of nonmetals. Okay, nonmetal elements are either colorless or they have various colors. So you can see bromine has a color, but these gases in the tubes here, they're actually colorless unless you shoot electricity through them. Then they light up like a neon light. They are non-malleable. You can't turn them into sheets. You can't hammer them. If you hammer them, they are brittle and they break. They're not ductile. They do not conduct electricity or heat. They're brittle when they're solid, and they're poor conductors. You would not use it to conduct electricity, and they are not magnetic. So the way I do this is I memorize what the metals are like, and then no, nonmetals are completely the opposite. It's a little trick of the trade. Metalloids are all solid at room temperature. They have some properties of both metals and nonmetals. They act like both. They're right in between, and they're mostly metallic in appearance. There's a picture of each. There's some of them right there. They're shiny. They look silvery, but they're brittle. So if I try to hammer it, if you look at GE there, it would break up like a piece of cement or chalk. Okay, I can't make that into a sheet. I can't make that into a wire. They are fair electrical conductors. Under certain conditions, they're really good. Under certain conditions, they're not. So we say they're fair. All right, so we're going to talk about chemical families on the periodic table. And it said, did you know that each column in my periodic table contains elements with similar properties? I'm a genius, I tell you. I can't do Russian accent. All right, chemical families is a group or column that contains elements with similar properties. My family, we kind of look alike. Dark hair, not super tall, good looking. So these are properties. They would put us in one vertical column because we have similar properties. So let's take a look at the periodic table and look at the properties that we're considering here. Group number 1, remember, hydrogen is not part of group number 1. It's just sitting there because they need to put it somewhere. Group number 1 is called the alkali metals. Let's take a look at the alkali metals from lithium down to francium. Now, this is a picture of someone cutting the metal. It looks like a big block of cheese. It's not, it's a metal. So this group of elements are all soft. You can cut it with a knife, it's weird. And they're silver colored. And they're all solid. They are all the most reactive, they are the most reactive of all metals because, and this gets a little complicated just because we haven't talked about the anatomy of an atom, but what I want you to see is that if we use the Bohr model of the atom, which is like the solar system, in the middle we have the nucleus and we have these little negative things circling, which is not exactly the right model, but it is a really good one to use to explain things. You can see that that blue dot at the end, there's only one blue dot. And what we see there it is, what we see is it's better to have a full ring than one that's just has one on there, okay? Those outer energy levels, or those orbitals, we call them orbitals, they should either have 8 is the number we're looking for, or if it's the first ring, like look at lithium, it should have 2. So that would be very, very, very stable. So they only have one, what we call valence electrons. 2 new words. Valence means outer, and electron are the negative parts that make up a part of the atom. So they only have one valence electrons. They very readily bond with other elements. They will attack elements like, here, take my electron, just get it out of here, by transferring their valence electron. They can't wait to get rid of it. You put it in water, it explodes. It's awesome. Really love, this is one of the reasons why I became a chemist. So we have the sodium electron. Chlorine, which is a nonmetal, tends to want to grab electrons. And so what we see is that the electron will be transferred from sodium to chlorine. And now we call these things we call these things ions. An ion just means that now we don't have the same number of positive and negative. We'll see that chlorine is negative and sodium will be positive because sodium lost its one negative electron. So meaning they have a full outer orbital. The bond between the ions create a substance that is new. And so I want you to take a look at this. We have sodium. I told you, you put that in water, it explodes. We have chlorine. It's a poisonous gas, like it's used in warfare. Together, they make a compound that is very safe and very stable. And it's called NaCl, sodium chloride. It's table salt. That is what we get from this thing, explosive in water and a poisonous gas, we get table salt. So I want to remind you, we're going back to that analogy of the elements make up everything we know, just like the 26 letters of a book, okay? 26 letters that make up books, I should say. You can't judge a compound by its elements. Like both these things would kill you, but together it's table salt. All right, alkali metals, they're reactive with water. I just said that. And to prevent contact with water vapor in the air, they're stored in mineral oil. So when I buy this, and I actually have some sitting somewhere on campus right now waiting for me, I have a jar with mineral oil in it, and inside that I have some sodium. Because it's so reactive, the water vapor in the air would react with it. Elements get more reactive as you go down the group. So we would see of these elements here, the one on the very bottom is the one that's the most reactive, and that is francium. And so francium is the most reactive, and it's also radioactive. Yep, it is just not stable. And I've never seen francium. I have a video attached. Please, 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 please watch that video. You'll like it, I promise. So on your periodic table, the group number 1, you should have written alkali metals. Alkali, it's a weird word, I know. Next, we have the alkaline earth metals. I did not name them. I would name it a name that's completely different. Oh well. Alkaline earth metals, family number 2. How are they similar? Well, let's take a look at them. The elements are also all silver colored, and they're all solids. Here's a picture down there of each one of them. They're also reactive with water, but less so than the element number 1, than the alkaline metals. They don't explode in water. They just get kind of bubbly. They each have, looking at these atoms, those blue dots are the electrons. I can see if I look at beryllium, that last circle has 2. Magnesium, the one that's furthest from the middle, it has 2. And calcium, the same. They each have 2 valence electrons, outer energy electrons. Okay, so they each have 2. You're like, so? Remember, it's stable when there's 8, or like in beryllium's case, there's only going to be 1 ring or 2. Okay, so we want to get rid of those outer electrons. They're not stable. They're sitting there kind of like a stack of books that's really high, and at the top you put a vase with flowers in it. That's not stable. Something's going to happen. Okay, so similar to group 1 elements, they readily bond with other elements. However, in this case, they transfer 2 valence electrons to become stable ions with full outer orbitals. Elements get more reactive as you go down the group, just like the alkali metals. Okay, so looking at this, I can see that radium would be the one that's most reactive, and you guessed it, it is also radioactive. Okay, not stable. Okay. All right, now we have the next family we're going to look at on your periodic table. Please, in number 17, put what's the name of them? They're the halogens. Sorry. The halogens are very reactive. This group of elements are all nonmetals, and they're found in all 3 states, solid, liquid, and gas. Okay. You can see fluorine and chlorine are gases, both very poisonous. Bromine's a liquid, and then we have the solids. Okay, they are the most reactive nonmetals because if we look at their electrons, again, we look at that outer ring, and there are 7 electrons. 1 more would make them super stable. 1 more, and they want 1 more electron to become stable. So unlike the metals who can't wait to tear off their electrons, they cannot wait to grab one and pull it in. Okay. So there's the 7 electrons. Oops, I was supposed to push that. 1 electron short of a full orbital, and they readily combine with other elements to take 1 valence electron from them to become stable ions with full outer shells. So I wanted to remind you, recall that when we talked about sodium and chlorine together, chlorine grabbed, sorry, what happened there? Chlorine grabbed that electron away from sodium, and that's what we see. These guys do not make good conductors of electricity because they're hanging onto their electrons. I want you to think of electricity like a flow, like a hose with electrons floating through. You have a hose, but metals are like passing the electrons on. Hey, here. Non-metals are like trying to grab them, so they would not let the electricity flow. All right, so halogens become more reactive as you move, surprise, up a group. Okay, so here are some examples of where we see halogens. We can see chlorine and bromine are used in pools. Iodine, maybe you use that on your skin to sanitize. And then down here, I'm not really sure what they're showing, but it is iodine, and the orange one is bromine. So the most reactive here is fluorine, and it is a kind of a greenish, yellowish gas, very poisonous. All right, halogens. The next one is the group 18. Please write in the noble gases, also called inert gases, but we call them noble gases now. And just like nobility, they do not want to mix with the riffraff of the rest of the periodic table. No, they do not. These non-metal elements are non-reactive gases. They're very stable. You're not going to believe why. I mean, you probably already know. You probably guessed it, but we'll wait till we get there. So here you can see if we shoot electricity through them, they make different colors, neon lights. And here's some other examples of where we see these elements. Helium is a noble gas, and you've probably sucked in helium and made your voice really high. It's really bad for you. Don't do that. They're non-reactive. They don't explode. You can't burn them. They don't burn. They don't want to react with anything. Okay, so they do not bond with other elements because they have they have a full outer orbital. So if you look at AR and NE, they both have 8 electrons. And then I did say that helium, for energy level 1, 2 is a full energy level, and it's full. They don't want to add electrons. They don't want to lose electrons. They're very stable. You can see the 2 for helium, 8 for neon, 8 for argon. And since they don't react with elements, they do not form compounds. Okay, they don't. And noble gases are also described as inert gases. Way back when I took chemistry in high school, we called them inert gases. This means they're non-reactive. All right, the next one group is the transition metals. Transition metals are, these groups contain metals that have the usual properties of metals. What? You know these metals. There's carbon, there's copper, not carbon, dude. There's copper, there's iron, there's chromium, there's gold, there's silver, there's mercury. You know these, platinum. Some of them you don't know, but the common ones are here, iron. All right, so here's the usual properties of metal, if you're asking what does that mean. And these metals are found in all the solid state except for Hg, which stands for mercury. That is the one liquid, which is a liquid at room temperature. We'd already talked about that. All right, so the transition metal contains some of the most commonly known metals. So guess these metals. Ooh, it's silver, it's jewelry. It could be silver, but it's actually platinum. Here we have some pipes. They're kind of orangey color. That's copper pipes. This looks like some kind of penny from Canada, copper penny. We have a cast iron skillet. Oh, dang. Spoiler. Iron, you guessed it. The next one, this is a light bulb, and it's a filament light bulb. And that means between those two standing up pieces of metal, there's this tiny piece of metal. That is tungsten. And we see those light bulbs still. In aircrafts, that would be titanium on the outside. We have some nice jewelry made out of gold. Oops. And the last thing is a silver goblet. Okay, so these metals, they are very common. And the last thing we have here is a mercury thermometer, the liquid metal. All right, the next family groups we're going to talk about, we're talking about vertical families right now, but I want to tell you that right now we're going to talk about these 2 rows that are at the bottom of the periodic table, and we do call them families. The first one that starts with number 57, starts with number 58, they're called the lanthanide elements, and they are all metals, and they've been misleadingly labeled rare earth metals. They're not rare, they're very hard to isolate though. And the actinide series, and these guys are the one on the very bottom. They're elements number 89 through 103. Remember, we're calling it a family even though we're talking about a horizontal. And these guys are, they're metals that are all radioactive, and they will spontaneously combust in air. So that is not a normal metal that we know of, okay? Our metals don't just combust in air. And I want to thank you. I can't wait to see you all again, and I hope you learned something about the periodic table. Thank you.